All right, this is AP, AB, and BC Calculus. We are doing Unit 4, Section 5, which is solving related rates problems. So more of what we did in Section 4, honestly. All right, so a small boat is being pulled to a dock by Popeye using a pulley. The pulley is 15 feet above sea level. If Popeye is pulling the rope at a rate of 15 feet per second, how fast is the boat approaching the dock at the moment when it is 8 feet away? All right, cool. Let's draw our diagram and label our rates. Sorry, I stayed up too late last night doing math. Okay, so there's a pulley that is, oh, that's terrible. It's not vertical at all, but whatever. There's a pulley that is 15 feet above sea level, right? So like here's the dock and there's the sea level. Yay. Okay, cool. All of my boats are sailboats because I can't draw. Okay, so that 15 feet can be labeled as a constant because the pulley's not moving, right? So a rope goes through the pulley and attaches to the boat, which we're just going to assume that the hull of the boat is actually at sea level, that I can't draw at all. It's fine. Okay. So basically what we have is a right triangle, right? We have a right triangle. I'm going to use B for boat, right? And I'm going to use this as R for rope. So Popeye, super strong guy that he is, I don't even know how to draw Popeye. He's like really big, strong arms, right? Like, woo, biceps. I don't know. That's kind of what I've decided Popeye looks like. Biceps. Okay, cool. He's pulling the rope this way, right? And when he pulls the rope, what ends up happening is that B is also going to change, right? The boat's going to move in this way. So we know that he's pulling the rope, dr dt, at a rate of 5 feet per second. But that's going to be negative because notice what my R represents, right? My R represents the amount of rope that is between the boat and the pulley. As Popeye pulls it, that rope gets shorter. So my dr dt should be negative, right? Because the R that I have in the problem is getting shorter. The R that I labeled, the distance of rope between the pulley and the boat, is getting shorter, right? So that's why dr dt is negative. And the thing I'm being asked to find is how fast the boat is approaching the dock. That's this. So that's going to be dB dt, right? So we're asked to find dB dt when, that's not how you spell the word when B is 8 feet, right? When the boat is 8 feet out from the dock, right? So that's my diagram and my rates. I need an equation that relates them. Not surprisingly, it's going to be Pythagorean theorem again, right? So B squared plus 15 squared equals R squared, right? I differentiate and get 2B dB dt plus 0 equals 2R dr dt. I would suggest you just divide everybody by 2 to make your life a little bit easier. Since this is the thing you're solving for, you could also just straight up solve for dB dt and recognize that when you substitute in, you're going to be substituting into dB dt equals R times dr dt, which are both values that we will know in a second, over B, right? So let's look at what we know. We know B, because at this exact moment, right, at this exact moment that they're talking about, B is 8. Well, 8, 15, 17 is a Pythagorean triple, right? Would be helpful to know that. If you don't know it, you could certainly use Pythagorean theorem to find that it's a 17, but we know B, we were able to find R, and we were given dr dt. So when I substitute, my dB dt is going to be R, which is 17, dr dt, which is a negative 5, because the rope is getting shorter, like the length of rope is getting shorter, over 8, right? Let's see, that's a 50 and a 35, right? So that should be an 85. So I get negative 85 over 8 feet per second. And then I have to answer the question. And the key here is that I was asked how fast it's approaching the boat. So, or approaching the dock, rather. So it is approaching at 85 eighths feet per second. And you could certainly turn that into a decimal if it's a calculator section. But the negative is because B is getting shorter. But the word approaching covers that, right? The word approaching implies that the boat is getting closer to the dock, right? So I don't need the negative in my answer. Cool. All right. P1. Ben Franklin is flying a kite in a thunderstorm. As you do. Totally sensible. The kite is flying horizontally away from Ben at a speed of 2 feet per second at an altitude of 40 feet. How fast is Ben letting the string out at the moment when the distance from his hands to the kite, meaning the length of the string, is 41 feet? Okay, so let's draw this thing. So here's Ben, right? We're going to neglect his height, right? So as a thing here, unless you are told otherwise, you're going to neglect Ben's height, which I know is crazy because, you know, he's not holding the string at ground level, but we're going to neglect his height and say that the altitude of the kite is 40 feet, right, and that this is a right angle. I'm going to use S for string. I'll use X for the horizontal distance. Here's a kite. Whee! Whee! Thunderstorm, yay! I probably shouldn't write over the problem. It's fine. Okay. So the kite is flying horizontally, right? Meaning dx dt, the change in the horizontal position of this thing. It's flying horizontally away from Ben at 2 feet per second. So that's dx dt. What we seem to want is how fast he's letting out the string. So we want this string coming out, ds, that says want. We want ds dt at the moment when the string is 41 feet, right? When the string is 41 feet out. So I need an equation. Well, that's going to be Pythagorean theorem again, right? So x squared plus 40 squared equals s squared. Differentiate to get 2x dx dt plus 0 equals 2s ds dt, right? I want ds dt, so I'm just going to divide everybody by 2s. So I'm going to go ahead and make this x times dx dt over an s equals my ds dt that I want. And when I go to substitute my specific stuff in, now I'm allowed to pay attention to the 41 feet. At this moment, we have a 9, 40, 41 triangle. That's another Pythagorean triple. They're not always going to be Pythagorean triples, but I am leaning heavily on them in these videos because I really want you to memorize the Pythagorean triples. So ds dt, it saves you so much time if a problem does involve a Pythagorean triple. They don't all involve Pythagorean triples, but a lot of them do. ds dt is going to be that 9 times the 2 all over a 41, right, which is an 18 over 41. So when I answer the question, he's letting out the string at a rate of 18 over 41 feet per second. Feet was my length measurement, and second was my time measurement. So I answered the question. All right, moving on. All right, so Fletch has just discovered that shadows are cool. When he moves his hands, the shadow moves too. No way. Side note, being 2 years old is fun. Fletch is 3 feet tall and is walking away from a streetlight that is 20 feet above the ground. Fletch is walking away at a rate of 1 foot per second. How fast is the tip of his shadow moving, and how fast is the length of his shadow changing? So let's draw this diagram. All right, so there's this lamppost. It is a constant 20 feet high, right? That's a constant. And there's a Fletch, and Fletch is a constant 3 feet high, right? So what happens is when a light shines behind you, your shadow is cast basically from the top of your head. That's the tip of your shadow. So what I want you to notice is that these are similar triangles. There's the lamppost triangle, right, which has this angle. And there's the little red triangle, the little Fletch triangle, that also has that angle and the right angle. So these are similar triangles. So that's going to be relevant, okay? So there's a couple different ways that you can do this. One way you can do this, right, is you could use one measurement to be the distance to the tip of the shadow. Okay, that's one way to do this. And then you could use, let's say, S for the length of the shadow, right? So S is the length of his shadow. So S is the shadow length. The other way I've seen this done, so that's one way to do it, but I think that's actually not the easiest way to do it. I think the easiest way to do this problem, the slightly better option, is to call this, we'll call this F, we'll call this Fletch's distance from the pole, okay? So the trick is that the length of his shadow is this whole thing, right? So that, or the tip of his shadow rather. So the tip of his shadow is at F plus S. It's how far he is from the pole, but also how long his shadow itself is. Okay, so let's walk through this. That's kind of the tricky part here. The setup for the equations is that they are proportional triangles. You have a 20 and an F plus S, and that has to be proportional to a 3 and an S. So that is 100% how you're going to set up this, this equation. The equation is going to be that 20 is to F plus S as 3 is to S. So if you cross multiply, you're going to get 20S equals 3 times the quantity F plus S. 20S equals 3F plus 3S, right? Essentially what that means, right, is that 20, sorry, not right, not 20, brain is tired, my bad. 17S is equal to 3F. So that's your equation that relates those two variables. So when I differentiate, right, I'm going to get 17 ds dt equals 3 df dt. Well, the first thing I'm asked in A, right, in A, I'm asked how fast is the tip of his shadow moving. Well, A is actually the harder question. B is actually the easier question. So B is asking me, what is ds dt, right? That's what B is asking. So let's do B first. So for B, when I go to substitute in, ds dt should be 3/17 of whatever df dt is, right? That should be 3/17 of how fast he's walking. So ds dt is going to be 3/17 times that 1 foot per second, or just 3/17 feet per second. Now that's great, okay? The trick with A is that it's actually easier. So remember that the tip of the shadow is f plus s. So if you want the rate at which the tip of the shadow is changing, that's going to be df dt, which we know is a 1, plus ds dt, which we just found in part B. So even though technically they're asked in the opposite order, it is easier to do this question in this order. So 17/17 and 3/17 would give me 20/17, right? So the tip of the shadow, so this is the length of the shadow is changing at this rate, right? The tip of the shadow is moving at 20/17 feet per second. And that's the answer to both parts of my question. So when you hear a shadow problem, it's almost always about proportional triangles. There's generally a lamppost. Sometimes the kid is walking towards the streetlight. Sometimes the kid is walking away from the streetlight. Sometimes it's not a kid. Sometimes it's a random person. But, you know, in this case, it was Fletch. Okay. P2. Bailey is not 2. He is a sweet old dog and doesn't much care about his shadow. Bailey is 2 feet tall and is walking towards the living room light that is 8 feet above the floor. Bailey is walking at 0.5 feet per second. How fast is the tip of his shadow moving, and how fast is the length changing? Now, we know from the last problem that it's actually easier to answer B first, right? Because you use B for A, right? We're going to use B to answer A. So let's draw this situation. So 8 feet up, there is a lamp in the living room. Bailey, who is 2 feet tall, is walking towards it. So I'm going to use B for Bailey and S for shadow, right? So again, we're looking at proportional triangles, right? So B plus S, the entire length of the shadow, right, is going to be proportional to, so 8 and B plus S is going to be proportional to this 2 and this S, right? Those are going to be proportional. We know that Bailey, so dB dt, Bailey is walking towards the light. So that's going to be a negative 0.5 feet per second because B is getting shorter. It's not about which direction he's walking. It's that he's walking towards the light. It doesn't matter whether it's left or right. So, because B is getting smaller, right? As he walks towards the light, the distance from him to the light is getting smaller. So my equation is going to be these proportional triangles. So 8 over B plus S equals 2 over S. 8S equals 2B plus 2S. 6S equals 2B. So S is 1/3 B, which means that when I differentiate, I get ds dt, which is what I want for answer B, is 1/3 of dB dt, right? So when I substitute in, the rate of change of the shadow is going to be 1/3 times this negative 1/2. So I'm going to get negative 1/6 feet per second. Now, I was asked how fast is the tip of his shadow changing, or, yeah, so how fast is the length of the shadow changing? So my answer to B is that the length of the shadow is shrinking at 1/6 feet per second, or I could have said changing and then included the negative, right? So if I put the word shrinking, that takes care of the negative for me. If I want to clarify that I should just say changing at a negative rate, that would be fine. When I go to do A, what we've seen before is that the tip of the shadow is this entire length, right? So the rate of change of the tip of the shadow should be the rate of change of b plus s, meaning it's db dt, which we had was a negative 0.5, plus ds dt, which we had was a negative 1/6. So that should be negative 1/2 minus 1/6, which is negative 3/6 minus 1/6, or negative 4/6, negative 2/3 feet per second. So if I answer the question, my bad, so to answer the question, the tip of the shadow is moving at either, you can say negative 2/3 feet per second, or you could say is approaching the lamp at 2/3 feet per second, right? Because again, if you're indicating the direction with your words, you don't necessarily have to indicate the direction with your sign, right? Okay. E3, you're at the dentist and the office has those little conical paper cups. Kind of wasteful, right? The cup has a height of 10 centimeters and a radius of 3 centimeters. You fill your cup at the water cooler. The water is entering the cup at a rate of 1 centimeter cubed per second. How fast is the water level of the cup rising at the moment when it is 4 centimeters? Okay, so let's do a diagram and some rates. Okay, so here's what we know. There are 2 cones in this problem. It might not feel like there are 2 cones in this problem, but there are 2 cones in this problem. There's the cup that has a radius that is 3 centimeters and a height that is 10 centimeters. But there's also the water in the cup, and that cone is changing because the radius and the height are going to depend on how much water is in the cup, right? These are also proportional triangles, which is going to matter in a second. So here's the reason that matters. I'm going to need the equation, so I'm given dv dt. The water is entering the cup. I can tell that that's dv dt. So dv dt, the water is entering the cup at 1 centimeter cubed per second. I can tell it's V because of the centimeters cubed, but basically what's happening is the water is going in the cup at a rate of dv dt, right? And we're trying to figure out, so the thing that we want is we seem to want dh dt. How fast is the height of the water changing when h is 4? That's the thing that we want, okay? So I kind of need to know the equation for the volume of a cone. So it's 1/3 pi r squared h. Now, sometimes this is given. Not always, but sometimes. So if it's given, dope, but I would suggest that you know it. Here's the problem. This has too many variables. If I differentiate this the way it is now, it's a product rule, because r and h are not the same thing, and that stinks and it's no fun. So what I need in this problem is I actually need a thing called an auxiliary equation. And this is going to happen when you have more than 2 variables in your equation and when you only know stuff about one of the variables. So what I want you to notice is that I really know nothing about r. R is not mentioned in this problem at all, right? So I really want to replace r. So I really want to replace r, because it's not even mentioned really, with h stuff. So the way I'm going to do that, and the way it's going to work in every cone problem, is that there are 2 proportional triangles. This water triangle, which has a height of h and a radius of r, is proportional to this cross-section of the entire thing that has a height of 10 and a radius of 3. So h is to r as 10 is to 3, right? Meaning if I cross multiply, 3h equals 10r. Since I want to replace the r stuff, I'm going to use 3/10 h to replace r. That's how I'm going to replace the r stuff. So my equation now is v equals 1/3 pi 3/10 of h quantity squared times an h. Well, that's a 1/3 pi times 9/100ths h cubed, or 3/100ths pi h cubed. Great. Now I'm going to differentiate that equation. So dv dt, no more product rule, is going to be 9/100ths pi h squared dh dt. Well, since I want dh dt, this is the thing I want, I know dv dt and I know h. So now it's really simple to substitute in. When I substitute in, dv dt was 1 centimeter cubed per second, and h is 4 at this moment. So 1 equals 9/100ths pi times 16 dh dt. I'm going to multiply by the 100. and divide by the 9 times 16. That's a 3 times 3 and a 4 times 4, so it's a 12 times 12. It's a $1.44 pi on the bottom. That's going to be my DHTT. If you want to simplify and cancel a 2, you certainly can, but honestly, I probably wouldn't. You could actually cancel more than a 2. You could cancel a 4. Yeah, that's the best you could do is cancel a 4. But still, I don't see a reason to do it. So my answer is going to be 100 over 144 pi, and its height, which was in centimeters, and its time, which was in seconds. So that's the rate of change of the height. So rate of change of the water level, right? And it makes sense that it's rising because the volume of the cup is increasing. Again, if you want to simplify the 100 over the 144, you certainly can cancel a 4. If you canceled a 4, you'd get a 36 on the bottom and a 25 on the top. So if you did this, that would also be right. Right? I'm just lazy. All right, cool. Let's do another cone problem. P3. PGW is tearing up South Philly streets to fix gas lines. Sand, to help fix the road afterwards, is being dumped into a conical pile at a rate of 4 feet cubed per minute. The pile has a height that is equal to its diameter. How fast is the height of the pile increasing at the moment when the pile is 5 feet tall? So, diagram and rates. So we have this conical pile. Now here you don't have the interior cup thing, like you don't have a cup measurement. Sand is being dumped onto the pile, dV dt, at a rate of 4 feet cubed per second. Okay, we know that we have a radius and a height, but that they are changing the whole time. There is no cup this time that has the same height and radius. So I know that my v is 1/3 pi r squared h, right? But again, I know nothing about r, so I really want to replace the r squared stuff. So there is no internal triangle here, but there is a line that gives me my auxiliary equation. My auxiliary equation says that no matter how this pile grows, the height is equal to the diameter. Well, that's the same as saying h is equal to 2r, and there's your auxiliary equation. So 1/3 pi 2, h over 2, my bad, h over 2 is r. So h over 2 squared times h. So I end up getting that this is a 1/3 times a 1/4, so pi over 12h cubed, right? Because that's an h squared and an h. So this is how I want to replace r, right? The reason I want to replace r is, notice I'm not given information about r, I'm given information about h, right? I'm asked how fast the height is changing, I'm given the height, I want to keep h. So you want to keep h, which says, hey, I need to replace r. Now when I differentiate, I get that dV dt is pi over 4, right, because it'd be 3/12 h squared dHdt, and I know all of that stuff. So when I substitute in, this is a 4 equals pi over 4, 25 is my h squared dHdt, right? When I solve for dHdt, I'm going to multiply the 4 over and get 16 equals 25 pi dHdt. So I'm going to get 16 over 25 pi equals dHdt, and then I'm going to have to remember to answer the question, right? My answer is that the pile height is growing or changing. You could just say changing at 16 over 25 pi. It was feet per minute. Let's check. Yep, minute. Right? And you could say growing, or you could just say changing. Remember, if something's positive, the sign isn't really in play that much. It doesn't matter. It's just you have to be mindful of those negatives. Like if something is shrinking and you say shrinking at a negative rate, that doesn't mean what you think it means. All right, E4. Using a time-traveling phone booth, Bill and Ted travel to the late Triassic period. Ted looks up and sees a pterosaur, which he refers to by the common name pterodactyl, when he says, Bill, dude, it's a pterodactyl. Whoa. Flying away at a speed of 10 feet per second and a constant altitude of 60 feet. At what rate is the angle of elevation from Ted to the pterosaur changing at the moment when the ground distance from Ted to the pterosaur is 25 feet? Okay, so here's Ted. Oh, we're going to assume that they're like, at ground level, right? We're going to assume that they trip out of their phone booth and they're on the ground, right? Always neglect the height of the observer unless you're told otherwise. I don't think I can draw a pterosaur, but we're going to try. They have like those long beak things, right? And then they have these like wings and they probably have some tails, right? Like, I don't know. I don't know what a pterosaur looks like. I think I just drew a dragon. It's fine. Okay, cool, cool, cool. So the pterosaur is flying away at a rate of 10 feet per second. So I'm going to use, oh, I don't want to use T for pterosaur. So we're going to use, we'll use X for this. So that's going to be dxdt, because T's and other T's get confusing, especially when you capitalize as inconsistently as I do. The altitude is a constant 60 feet. Right, so that's a constant. We can assume the ground makes a 90-degree angle with the vertical unless we're told otherwise. And we are asked about the angle of elevation, right? So again, we're neglecting the height of Ted, and that's fine. So so what we want, right? We want the angle of elevation is changing at the moment when the ground distance from Ted to the pterosaur. So we're saying we want d theta dt at the moment when x, the ground distance, is 25 feet, right? Not the direct distance. Okay, so cool. So let's find an equation, right? This is my diagram and my rates, right? And there's no really good way to label d theta dt. It's the way that the angle is changing. So the equation that relates theta and x and 60 is probably going to be either tangent, which is fine, 60 over x, or honestly, cotangent might be slightly easier because then your x is on top. So I'm going to suggest that you probably want to use cotangent of theta equals x over 60 because it's a lot easier if the x is on top. You don't have to use the quotient rule or a chain rule. It's up to you, though. When I differentiate, right, the derivative of cotangent is negative cosecant squared theta d theta dt, right? And on this side, I'm going to get a 1/60th dx dt. So now I need to solve for d theta dt. So you don't have to solve first, but I'm going to suggest that it's a little bit easier to do so. If you notice that this is a 1 over sine squared, it's a little bit easier, right? So I want d theta dt. I have this 1/60th dx dt. I'm going to multiply the negative sine squared over it. I'm going to get the d theta dt equals a negative sine squared theta times this 1 over 60 times whatever dx dt is. Well, we know dx dt, and in the moment that we're being asked to substitute, we know that this is a 25 and this is a 60. So we can find the missing side, right? So like this is a picture, right? The whole thing is a video. It's changing at all times, but this is a picture. So I can find, I'm just going to use d for distance here. I could find the distance. So the distance would essentially be the square root of a 25 squared plus a 60 squared. Now, if I don't have a calculator, I'm just going to have to deal with that, and it's not awesome, but it is what it is, okay? So, and I could also figure out what they are, but let's just not deal with that yet, and we'll cross that bridge when we come to it. So when I substitute in, I'm going to get, so remember, sine is this thing over this thing, right? So I'm going to get negative 60 over this square root, which we'll deal with in a sec, quantity squared, times a 1 over 60, times dx dt, which was how fast the pterosaur was flying, which was 10, right? So 10. Cool. So if we clean this up a little bit, I'm going to end up with a 60 times a 60 on the top. I'm going to end up with the bottom just being this expression without the square root because the whole thing was squared. I can cancel one of the 60s and its time is at 10. Now, if you have a calculator, great. If you don't have a calculator, here's where you're at and you just deal with it, right? So d theta dt. I seem to get a 600 on the top. On the bottom, I really don't feel like doing 25 squared and 60 squared in my head. 25 squared is definitely 625. 60 squared is definitely, oh, never mind, it's fine. 625. Plus 6 squared would be a 36, so this is a 3600, right? So you should get that this is 600 over a 4225, probably. And we can double check that because my brain is tired and I do stupid things sometimes. What was it, 60 squared? Cool. Hey, there we go. All right. So great. You can simplify it if you want. If it's a calculator section, you would not have done all this mental math. You would have been typing in the first place. So that's fine, right? Yeah, you can, again, if it's a non-calculator section, you're going to be leaving it as a pretty ugly answer. And if it is a calculator section, you're going to be typing. So there's not a whole lot of reason for you to be killing yourself on this. So I'm going to get that this is 0.142. And our angles are always in radians, and in this problem, our time was in seconds, I think, but we're going to go up to check. 10 feet per second, so time per second. So your angles are always in radians in calc. Okay, and there you have it. All right, cool. In an attempt to flee the Triassic period, Bill and Ted land in the late Jurassic period. When they exit their fantastic phone booth, they trip and look up to see a massive Brachiosaurus approaching them. It is lumbering towards them at a rate of 4 meters per second. If the Brachiosaurus is 9 meters tall, essentially, so tall, right? How fast is the angle of elevation from Ted/Bill to the top of the Brachiosaurus changing at the moment when the dinosaur is 40 meters from them? So, they trip out of their phone booth, right? Like, they fell down. There's Bill, there's Ted, there's a phone booth. It's great. Okay. If you don't get the reference, by the way, it makes me sad. Okay. So, there's a Brachiosaurus. Whee! I don't know what a Brachiosaurus is going to look like if I draw it. It's got a really, like, dog-like tail, but it's fine. Okay, here we are. Great. Okay, cool. All right, we know that this is 9 meters and it's constant. I'm going to go ahead and use, we'll use B for Brachiosaurus, right? And he's walking this way. So what that means is that dB dt, he's lumbering towards them, is a negative 4 meters per second, right? Which is pretty fast, but he's got really big legs, so, you know, for him it's short steps. The reason it's negative is because he's getting closer to them, right? And we're being asked about theta, right? So we're asking the thing that they want. This is my diagram and my rates. The thing that they want is d theta dt when B is 40, right? So my equation is going to probably be, again, cotangent. It seems like the easiest option. So cotangent is going to be B over 9, right? The reason it's the easiest option is it's easier to have your variable on top. So I get negative cosecant squared theta d theta dt equals 1/9 dB dt. If I clean this up a little bit by solving, it's basically the exact same situation. This is the same as a 1 over sine squared, right? So I'm multiplying by a negative sine squared. So I get d theta dt equals a negative 1/9 sine squared theta dB dt, and then I'm going to find all those values. So at the moment when I'm substituting, and this one's a little friendlier than the last one because I gave you a Pythagorean triple, 9, 40, 41 is a Pythagorean triple. So at this moment, right, the sine of this thing is going to be 9 over 41, right? So I'm going to get that when I substitute, my d theta dt is going to be a negative 1/9 times a 9 over 41 squared, but I'm just going to write it as a 9 over 41 times a 9 over 41 so I can cancel some 9s, times how fast this dude is walking there. So that's going to be, one of the 9s cancels and the negatives cancel, and I seem to get a 36 on top of whatever 41 squared is, which I don't feel like doing. 1600 and a 40 and a 40 and a 1, so 1681 is what I'm going to come up with, but we're going to find out in a second because I'm tired and my brain is not awesome. Hey! All right. For the record, what I did to square 41 was 40 plus 1 times 40 plus 1. I foiled. So, if you wanted to do this as mental math, that's what I did. And I got 1600 and a 40 and a 40, which was an 80 and a 1, hence 1681. So when I answer the question, I'm just going to leave my answer as 36 over 1681 unless it's a calculator section. If it's a calculator section, you can definitely put the decimal equivalent, right? Like you could absolutely put 36 divided by 1681. Please don't do a ton of mental math if it's a calculator section. That's just a miserable experience for everyone. So that's not super duper fast. So that's, oh, it's not meters per second. Come on, brain. It's radians per second. It's the angle. Pay attention, Hogan. So it's radians per second. So, so we get that this is approximately a 0.021 radians per second, right? And that's a quick save that you got to be careful about. Like I just accidentally got an autopilot and put that it was meters, but it's not. It's the angle, so it's radians. All right, let's do 2 more problems, and then that's it for this video. All right, not a word problem. It happens, although most related rates problems are. So we're given this equation, we're given what dy dt is, and we're asked to find dx dt when y is 1. So we don't have to do diagram and rates. They're gone. You already have the equation, right? So you've already got the dre part is over. You just have to do the dsa, right? You have to derive, you have to substitute, and then you have to answer the question. So when I differentiate, right, this is going to be a product rule, which is going to matter. So I get derivative of x squared is a 2x dx dt, right? Then when I do my product rule, it's going to be u dv is going to be a dy dt, plus v du is going to be a 3 dx dt. And when I differentiate the y squared, I'm going to get a 2y dy dt. And when I differentiate the 1, I'm going to get a 0. So that's disgusting, but here's the thing. I know some of these values. I know dy dt, so I know that, and I know that. I know y, so I know that, and I know that. The only thing, and I want dx dt, right? So this is the thing I want. The only mystery thing that I really need to find these x's. Well, the way I'm going to find the x is by saying, oh, I have an equation, x squared plus 3x times the y value plus the y value squared is 1, x squared plus 3x equals 0. So it turns out that there are two possible x values here. X is either 0 or x is negative 3. Since there are two x's, there are going to be two answers for dx dt, and you're going to have to find both, right? So basically, here are my 2 points. When I substitute, I'm going to substitute twice. I'm going to do 0, 1, and I'm going to substitute negative 3, 1. There will be two answers. So let's go back up for a second and see if I can. All right, so when I plug in 0, 1, right, I'm going to get anything with an x is going to be 0. So that one's actually the easy case because these two will both get wiped out. Plus, this is going to be a 3 times the thing I want, dx dt, right? Plus a 2 times y times whatever dy dt was, which was a 2. And that's going to equal 0. So I'm going to get 3 dx dt equals, this is a 4, right? So negative 4 when I add it over. So I'm going to get that dx dt is a negative 4/3. So that's one of the two answers, right? So that's the answer I get. So that's the answer I get when I use 0, 1. Now I'm going to have to do the same thing, but I'm going to quickly drag this picture down because otherwise I'm going to be kind of miserable. So let's drag this down. All right, so when I go, let's make this slightly smaller because I don't need it to be quite that big. All right, there we go. Just needed to be able to see it. So when I substitute into this for the second one, so that's one of my two answers, the second answer is going to be what happens when I substitute in these values. And this one's less fun because now you have an x that's actually a number. So this is going to be negative 6 times dx dt, which is the quantity I want to find, right? Plus, this is a negative 9 times 2, because that's what dy dt was, right? Plus, this will be a 3 times the thing I want to find, right? And then this is still a 2 times 1 times 2 equals 0. So I seem to get negative 6 dx dt, right? This is a negative 18, and this is a plus 4. So that seems to net a negative 14 plus 3 dx dt equals 0. So I seem to get negative 3 dx dt equals 14, which means I get dx dt is 14 over negative 3, or negative 14/3. So there are two answers here because there were two x values that gave me the y value I need, right? All right. Last one, P5. Go ahead and pause me if you want. It's the same situation. It's up to you, but I would argue that knowing that you need the x at some point, you might want to just go ahead and find x. You're going to need the x at some point, so you're going to get x squared minus 2x minus 1 equals negative 1, so x squared minus 2x is 0, so x is either a 0 or a 2. So there's going to be two answers, right? So there's going to be two answers when I'm done. I need to do both of those answers. So knowing that, now let's go ahead and differentiate. So I don't need a diagram or a rate because there aren't any, right? This is just an equation, and they gave me the equation. When I differentiate, remember that this is going to be a product rule. So derivative of x squared is 2x dx dt, right? And then my product rule, so u dv will be a dy dt, plus v, which is y. du is going to be a 2 dx dt, right? Plus 3y squared dy dt, and on the other side, it's going to be a 0. So now I know all of this stuff, especially because I bothered to find the x first. So I want to find dy dt, right? That's the thing I want to find. And I know everything else. So I want to find this. There's going to be two of them, and I just plug in the numbers, right? So when I substitute, I'm going to have to substitute 2 times, right? I'm going to have to substitute for the point 0, negative 1, and that's going to be the easier one because all of the x terms are going to get wiped out, right? So that's going to be 0 plus 0 plus, this will be a negative 2, right, because it's negative 1 times 2, times dx dt, which was a 3, plus this will be a 3 times a regular 1, because you're squaring it, times the thing I want, equals 0. So I seem to get negative 6 plus 3 dy dt equals 0, so 3 dy dt equals a 6, which means in this case I get dy dt equals 2. So that's the first answer, the one I get when I substitute in 0, negative 1. We're going to do the same thing here where I screenshot this so that I can drag it down, because otherwise it's going to be a fairly miserable experience to try and copy it all from scratch. Okay, cool. So then I'm going to go ahead and substitute in the other value, right? So now I have to do this same thing, but for the point 2, negative 1. So now when I substitute in it for 2, negative 1, well, now my x stuff doesn't go away, so it's a little bit harder. So this is going to be a 4, because it's 2 times 2, times dx dt, which was a 3, right? Plus a 2 times 2, which is a 4, right? Times dy dt, which is the thing I want to find, right? Plus essentially the rest of the problem stays the same. So a 2 times a negative 1, which is going to be a negative 2 times that 3, right? Plus this will be a 3 times the dy dt that I don't know. So those pieces actually stay the same. So I end up with, this is a 12, this is a minus 6, so I end up with a 6 plus 7 dy dt, right? Because there's 4 of it and 3 of it equals 0. So I end up with a dy dt that equals negative 6 over 7. And notice that there aren't units here. There weren't units in the last problem. It's not a word problem. It does not have units. And that rather lengthy video is our Unit 4, Section 5.